Hi, hello everyone. Welcome to my channel IB Crocodile, where I provide supporting academic videos for both mathematics and physics. During my 25 years career of tutoring in different countries, I had the privilege to be exposed to many different systems, like American system, British system, GCSE, IGCSE, SABIS system, Canadian diploma, then IB diploma. So I decided this video, I would like to talk about the math conventions for the number sets. Okay, I would like to share my experience to define the number sets in different systems, with the special focus today on what is on the IB curriculum. Okay, so today is the number set conventions according to the IB diploma. Okay, so let's have fun. Okay, so let's go through the number sets conventions together. So the first set started way back when you started to count. I don't know at what age you started to count, but a long time ago. So you started to count. What did you start to say? 1, 2, 3, 4, and so on. Okay, so this set here is called the set of counting numbers. Okay, so counting numbers 1, 2, 3, point until positive infinity. Okay, now the next one is called the set of whole numbers, and this set is mainly used in the American and Canadian system. So the whole numbers is a set denoted by capital W, and it is basically the set of counting numbers including 0. So W is 0, 1, 2, 3, point, positive infinity, right? And this is the set of whole numbers according to the American and Canadian system. So if you are an IB student, don't worry about the whole numbers. You are not going to deal with whole numbers. You are going to deal with integers, which is my next set. Okay. So, and of course here there is whole numbers does not include any negative numbers. So when we grew up at school, like from elementary school or junior high, we started to deal with negative numbers, and that's why there is a need of the deal or develop the set of integers which will include the negative numbers, are still integers. So the integers z, right, is basically 0 in the middle, and then 1, 2, 3, point, positive infinity, and on the other side, -1, -2, and -3, point, negative infinity. Okay, so there is nothing between 1 and 2. There is no numbers between 1 and 2 in the set of integers, right? Because they're just integers, right? So, and then what we did, we took 1, 2, 3, point plus infinity, and we call them positive integers, and then -1, -2, -3, negative infinity, we call them z negative, or the negative integers. That leaves us with a 0 in the middle, because 0 is neither positive nor negative, right? So z positive here is just a positive integer. So if the question involved dealing, or let's say x belongs to z plus, okay, so 0 is not included. You cannot consider 0 in the question if the assumption in the beginning of the question, for example, mentioning that okay, x belongs to z plus, so there is no 0, there is no negative integers, right? And that's why there are a couple of sets are being developed now, which is called the non-negative integers. So when I say non-negative integers, it means the positive integers and 0, because 0 is non-negative, right? So the non-negative integers is basically the positive integers union the set including the 0, one element. And then with the same way, right? The non-positive, so non-positive integers is going to be the negative integers including 0, right? So it's going to be z negative, because 0 also is not positive, right? So the non-positive integers is z negative union the 0. Okay. So far we covered the set of counting numbers, whole numbers for Canadian and American systems, and the set of integers. This is in IB diploma, the same definition, okay, the same convention. Now, in the IB diploma now, there is an adoption of another set, and they give it actually like letter N, big letter N. And they say, okay, in the textbooks, so the N is basically the non-negative integers. So N 0, 1, 2, 3, point, positive infinity. Okay. So now the question here is, N is the set of natural numbers. We do not call it in the IB program natural numbers. Even in the SAT, in the SAT American system, there is no mentioning about natural numbers. We deal only with whole numbers, integers, counting numbers, and so on. Why? Because there is a controversial, there is no a standard agreement about, among mathematicians about the natural numbers. Okay, there are some opinion, there's certain opinion that says no, the natural numbers, because when you count naturally, right, you started with 1, not 0. Okay, so there's one opinion saying 0 is not a natural number, right? And then, okay, so the natural numbers should be 1, 2, 3, point, positive infinity, right? Whereas on the other hand, in the case of absence of objects, so the 0 is representing the counting case if there is no objects. So this is the controversy. So the other opinion that says natural numbers is actually 0, 1, 2, 3. So whether you agree with this or that, it doesn't matter here, because we don't even call it natural numbers. They give it N. And I think it's a bit confusing to use N as well, honestly. But yeah, but anyway, if you see in the question anytime, anywhere that X belongs to N, so N here is that represents the set of non-negative integers. The non-negative integers, okay, 0, 1, 2, 3, point, plus infinity. It is not the natural numbers, okay, it's not the set of natural numbers. We call it just N. Okay. And this is IB. This is the definition. This is included in the IB textbook, and in many questions, especially in proof by induction. Okay, you need to know where is or what is the starting point. If X belongs to N, so the starting point actually is 0. If X belongs to Z plus, the starting point or initial condition has to be 1, not 0, because Z positive is only positive integers. So I have to start with 1, not 0. Okay, so I hope I made that clear with minimum confusion. So let's move on. So then later on in the game, you started to deal with fractions, you started to deal with ratios. So the set of integers actually, is not helping, could not help if you have to deal with fractions or decimals. So what if between 1 and 2? What is you know what to do. So that's why we develop the set of rational numbers and we give it a symbol of Q capital. So then the rational numbers by definition is the set of all A over B such that A belongs to, this symbol here means belongs to, I'm going to talk about this later, so in a minute. So A belongs to Z. So Z here is what? Is the set of integers. So A has to be an integer, B has to be an integer, and then B cannot be 0. Okay. Now let's talk first about this couple of symbols here. You know, this symbol here means belongs to or is an element of, and the bottom one does not belong to or is not an element of. So these two symbols are used to describe the relationship between an element and a set. Okay, so an element and a set. So an element would be on the left hand side, and any set would be on the right hand side. Let's have some examples. For example, when I say okay 2 and then I put Z, okay, set of integers. Now I want to choose between these two symbols here, belongs to or is an element of or no, right? Now you ask yourself, is 2 is an integer? Yes, so we're gonna use belongs to, right? But for example, when I say 1.5, so 1.5 and I put Z, so 1.5 is not an integer, obviously. So in this case, I need to use does not belong to or is not an element of. Whereas if I put 1.5 and then Q here, right? So the answer here, or the symbol to be used, is yes, it does belong to Q, because 1.5 is a rational number. Why? Because you can actually put 1.5 as 3 over 2, right? Now 3 over 2. Now let's look at the definition. Okay, does 3 belongs to Z? Yes. 2 belongs to Z? Yes. Is 2 equal 0? No, the denominator is not 0. So this satisfies the definition of a rational number. So 3 over 2 or 1.5 belongs to Q. Now, why we avoid dividing by 0? The answer is simple. In mathematics, okay, anything divided by 0, anything divided by 0 is called undefined quantity. Okay, until you finish university. Okay, anything divided by 0 is called undefined quantity. And even if you try using the calculator, you divide by 0, you get an error or some message telling no, this is undefined quantity. So that's why we cannot have 0 at the denominator for any rational number. Now, I want to also elaborate on the decimal representation of a rational number. So there are two cases where a decimal number can be considered or is classified as a rational number. The first case, if the decimals are terminated. So if it is terminated decimal expression, okay, let me just get some space here. So if it is a terminated, let's say 0.5. So 0.5 is a terminated decimal number. There is nothing after 5. And obviously we can say, oh, this is 1 over 2, right? So this is a rational number, belongs to Q. Okay. 0.2, which is basically 1 over 5. Yes, it belongs to Q. So this is the first case. Now the second case, let's say 5 over 7. Okay. So if you divide 5 over 7, you know what you get. Okay, let me just put it a little bit down so I can have some space here. So 5 over 7, okay, is going to be 0.71428, 5, okay, 71428, and so on. So this is actually non-terminated but repeating decimal, or sometimes you call it a recurring decimal. Okay. So you can see here 0 point, so I mean the digits after the decimal point 714285 repeats again 714285 and so on. So actually we can actually rewrite this number as 0.714285 and then you could put bar on the repeated decimal. Okay, so this number is also considered as a rational number, so it belongs to Q. Okay, so these are the two cases, the decimal expressions that are that can belong to that can be classified as a rational number, so they belong to Q. Okay, terminated decimal or non-terminated but repeated, recurring. Okay, so then the question or the natural question now to be asked, okay, what if it is, what if the decimal expression is infinite but then also non-repeating? So in this case it doesn't belong to Q, and in this case we will call it irrational numbers. Okay, now some textbooks, especially in American system and British system as well, they call it Q prime. In the IB diploma they don't give it actually a name. They just say, they call it just irrational numbers. It's okay, it's not big deal. Okay, I mean, I prefer Q prime because I have seen it before in other systems. So Q prime is the set of irrational numbers, right? Like for example, square root of 2. Now square root of 2 is going to be an infinite, even if your calculator give you, for example, 6 or 7 or 8 decimal, you know, if you change the system or the settings of the calculator and you allow more decimals, you will get more decimals. So root 2 basically is irrational number, right? It has non repeating and also infinite decimal presentation. Okay, another example is pi, right? Is the constant. Okay, so also it is irrational number. Okay. Now, if I would like to express the rational numbers and irrational numbers like as Venn diagram, right? So how can I express them? You know, like if I draw a circle, right? And let's say this circle is Q. Okay, where can I put Q prime? Is it like, is going to be overlapping, is going to be inside, or is going to be like a disjoint set? So the answer, of course, is going to be disjoint, because a number cannot be rational and irrational in the same time. Okay, so this is called Venn diagram. So we can represent sets with different elements using, you know, circles and rectangles or shapes, right? I mean, most common is basically circles and rectangles. So this is Q, and this is going to be Q prime, right? So I can put pi and root 2 here, right? And then I can put, you know, whatever, like 1/8 or 2 even. I can even put 2. Why? Because 2 technically is a rational number as well. Why? Because 2, we can rewrite it as 2/1. 2/1 is a rational number, so the denominator belongs to Z. Denominator is not 0. So 2 also is a rational number. So that means what? That means actually all integers are inside the set of rational numbers, because you can write any integer number as over 1, right? Which means the set of integers is a subset of the set of rational numbers. Okay, I'm going to elaborate a little bit about that, but I mean, now we have Q and Q prime, or the set of rational numbers and the set of irrational numbers, right? So the union of these two sets will give us what we call the set of real numbers. Okay, so the set of real numbers, okay, this is actually the diagram here. So R, the real numbers, now is going to be everything, you know, including Q and Q prime. So the definitions of real numbers is rational numbers union Q prime. Okay, and as you see here, you know, so this is the irrational numbers and this is the rational numbers, right? But then you can see also the Z as integers, as I mentioned, they are subset of a rational number, and then, or basically a proper subset. I'm going to elaborate again 1 second. And then n, this is IB textbook. IB textbook. N, it's not natural numbers, but just 0, 1, 2, 3, point, positive infinity. Okay. So, and obviously also sometimes we express the set of real numbers as the number line. So the number line here has represent the set of real numbers, 0 in the middle. Now between any two numbers on the number line, there is an infinite number of numbers. Okay, because there is infinite number. Can be rational, can be irrational, can be infinite decimal, whatever, repeating, non-repeating. So R, or the real numbers, include all these sets. Okay. Now I would like just to elaborate about also the use of these couple of symbols. So this symbol here is called a proper subset, right? And this symbol here is called just a subset. Okay, and sometimes you may also see subset or equal because of this equal sign below. So let's talk first about subset or equal. So if any set, like let's say set C, right? So has, for example, let's say elements 2, 3, and 4. Okay. And then another set D has also the same elements 2, 3, and 4. Right? So that means all the elements of C are also exist in the set D. So now we can say C is a subset or equal to D, or I can say also D is a subset or equal to C. Okay. But now the other symbol here is called proper subset, and by definition is the set that is contained also in a larger set and does not contain at least one element. Does not contain at least one element of the larger set. For example, when you look, for example, at n, which is 0, 1, 2, 3, right? Now there is a larger set, which is the set of integers. Now there are some negative integers here. They are not in the smaller set, right? So in this case, I have to use this symbol here without or equal sign here. So now I can say, I can now present a relationship between two sets, right? So between two sets, so I can say N is a subset of Z, right? And also, and I can say also Z is a subset of Q, right? Because as we discussed, all integers also belongs to Q because all of them can be over 1. Now, can I say Q is a subset of the set of the real numbers? Of course, I can say that, right? Now, how about like switching? Like, can I say, for example, Z is a subset of N? Of course not, because Z is larger than N, so we can say is not a subset. You can just use the same symbol with a slash, crossing through it. Okay, so this symbol here is called a proper subset, right? So when the set is contained in a larger one, but then at least one element, is not contained in the smaller set, or it does not contain at least one element of the larger set. Okay. Now, the next set, just to complete the story, is the set of complex numbers, and this is not included in the standard level. If you take IB standard level, you will not deal with complex numbers, but if you are high level, so you will deal with complex numbers. So let me just quickly highlight on, just to give you some highlights on the complex numbers. So the complex numbers, they have like a symbol C, big C, and there are many presentations of the complex numbers. I will just talk about the Cartesian form. So complex number is a plus bi or x plus yi, whatever. So this is called the complex, or sorry, the Cartesian expression or Cartesian form of a complex number. So where it came from? So it came when we deal with some negative under the square root. So for example, when I say square root of 4, right, that actually refers to the principal positive square root of 4. So when you see this symbol here, square root of 4, it means only one value, which is the principal radical, right? And it's going to be 2. Okay, this is by definition. But then if you face a square root of negative 4, right, until your knowledge of the real numbers, you are not able to deal with this. Okay, so we need to know another set or another concept to deal with negative numbers under the square root. So we can say, I can rewrite this as root 4 times square root of negative 1. You can combine over multiplication or division under the square root is fine. Okay, and then square root of negative 1, we call it I, or the imaginary number. So this is imaginary, not real. This is imaginary. So then here is going to be root 4 is 2, root minus 1 is I, so root negative 4 is 2I. Okay, as a complex number. Okay, and where I is the imaginary number. So now let's have another example. Let's say a complex number. Let's say, I don't know, 1 plus 2I. So this is just a Cartesian form of a complex number. Now we call this the real part. So 1 here, or A, or whatever the symbol here used, X or A. Okay, this is called the real part. So here 1 is called the real part, right? And then 2, the coefficient of I, again, the coefficient of I, the number multiplied by I, not 2I, just 2, is called the imaginary part. It's called the imaginary part. Okay, so now sometimes the B equals 0. Like in case of B equals 0 as imaginary part, we come back to only a real part, right? So if the imaginary part is 0, right, if B equals 0, so now that complex number become real. And that's why I can also say that the set of real numbers is a subset of the set of complex numbers. Okay, now let's go through just one example here to consolidate our understanding. So let's have a look at this. Circle the real numbers and underline the integers in these numbers here. Okay, so circle the real number. So 3.75. 3.75, okay, is a real number, right? So we can circle that. Okay, so the real numbers contain almost everything except imaginary numbers. So 3.75 is going to be a real. 1.33, so this is recurring. So this is actually a rational number, but rational numbers are real, so it's fine. Root 25, square root of 25 is 5, and 5 is an integer, but then anyway, if integers are part of real numbers, so I can circle that. Root negative 7, this is imaginary. I cannot circle because now negative under the square root, you know, this is complex. Now negative 2 over 5, sure, rational or real. 56 over 7, real. Absolutely, 0 is a real number. Now let's underline the integers. Okay, so 3.75, obviously there is a decimal part, it's not an integer. 1.333 also is not an integer. Root 25 is 5, so this is an integer. 56 over 7, which is 8 simplified, so 8 here is an integer, and 0 of course is also an integer. Okay, by this I conclude my video for today, and if you like it, you consider subscribe to the channel and share with your friends. Thanks for watching, and see you in further videos.